So let's kick it off. Thanks everyone again for joining us today in our October meetup. For those of you who join us for the first time, this is the Data Science on AWS meetup. Chris Fregly and I, Antje, Barth, we're hosting this monthly, and we co-authored together. Hi, Chris. We co-authored together the Data Science on AWS O'Reilly book. And we're also running those community meetups every month. And we're super excited to talk about everything data science, machine learning, AI. We're super excited to host guest speakers every month. And we do have a really good lineup today, an exciting one for you as well. So you found the meetup group, otherwise probably you wouldn't be here today. For those of you who want to check out also, we do have the agenda up for next month, for November, with a packed and exciting lineup of speakers there. But let's have a quick look what we're talking about today. And we do have 3 sessions today, so it's going to be packed. We're going to start here in a little bit with the team from Linea. We do have Doris Sin, founder, and Andrew Kui here with us, software engineer at Linea. And they're going to talk about messy code to clean pipelines with Linea Pi. So super excited to see an introduction and a demo there from the team. And then we do have also speaker from NVIDIA, Neil Vaidya, technical marketing engineer. He's going to talk about how to run distributed JAX training with Ray on NVIDIA GPUs and Amazon SageMaker. So excited to see that demo as well. And we also have Ganapati here from AWS, who's going to show us how to integrate Amazon SageMaker Data Wrangler, our data preparation service here at AWS, with MLOps workflows. So those are our talks for today. And without further ado, I'll hand it over to Doris and Andrew, who will introduce us to Linea and Linea Pi. So I'll do a quick stop screen share here, making sure I press the right button. All right, Doris and Andrew, welcome very much. And thanks for joining us today. And yeah, take it away.
Thank you so much, Antje, for having us as well. So my name is Doris. I'm the founder and CEO at Linea, which is a seed stage MLOps startup. We are currently working on an open source project called Linea Pi, which we're going to tell you a lot about. In a past life, I was a PhD at the Rice Lab at UC Berkeley, working on topics related to Linea Pi. And here with me today is Andrew, one of our software engineers. Andrew, quick intro.
Sure. I'm Andrew. I worked in data science and ML for probably like 3.5, 4 years now. And yeah, passionate about what Linea Pi can do to help data science.
Awesome. All right, let's dive into it. So all right, so here's a quick outline of what we're going to talk about. First, we're going to give a quick overview of the Linea Pi solution. Then we're going to dive straight into a demo with Andrew. Afterwards, we're going to talk a little bit more about the different use cases for Linea Pi. Then we're going to dive deep into the Linea Pi abstractions to kind of show folks how the magic happens. And then we'll close out about talking about integrations, specifically focusing on one of the integrations that we're working on right now, which is MLflow. All right, so I think folks are really familiar with data pipelines in this room and understand that data pipelines are everywhere and they are the key driver for what happens in the data science world. The issue that we're trying to solve with data pipelines is that today we're seeing 2 very siloed stacks for data science and development and production, right? On the development side, we see tools like Jupyter Notebooks, Pandas, and all of these Python data science libraries that data scientists have learned in school and are really familiar with, and they can work very quickly with those tools to be able to get at data insights really quickly. But once that development is done, there's a whole process of translating what's happened on that side into this other stack on the production side that cares a lot about a very different set of concerns, right? Like on the production side, we care about stability, reproducibility, scalability. And right now, there really isn't a very formal process of going from what happens on the development side to the production side. And because of that, we're seeing some pretty major problems in this process. The first one is that it takes a long time to refactor the development code, which can usually be very messy because folks are working very quickly. Notebooks are notoriously easy to have out-of-order execution and other irreproducible behaviors. And then the second thing is that folks working on the development side have to learn new frameworks and context switch to be able to work with the stack on the production side. And lastly, they have to rewrite their development code into data pipelines using the production stack, right? That is really cumbersome because it takes away time from data analytics, and it's also redundant because fundamentally the two pipelines, the two workflows on the development production side are the same. We're just asking folks to express them using different languages and different frameworks. So what Linea Pi is trying to do is we want to streamline the process of going from development to production by abstracting away a lot of the concerns of code refactoring, translating data pipelines. And at a very high level, the solution looks like this Python library that you import into your development environment. And it then runs in the background as you work, capturing everything that you do, analyzing everything that you do. So by the time you do get to an interesting artifact, which can be a model, can be a data set, can be a chart, can be anything that a data scientist is interested in, we are automatically doing three very important things. The first one is we're automatically capturing lineage. So we understand the relationship between, say, the training data and the model, two data sets that have transformations happening to transform one to the other, so on and so forth. And the second thing that we do is we can automatically refactor development code into something that's a lot more clean, that's a lot more modular, right? A lot of times what happens in development, really only 10% of that is something that data scientists want to keep and put into production. And Linea Pi can automatically help us extract out that 10%. And lastly, Linea Pi is able to automatically construct data pipelines from raw Python code. So imagine that if you can just take a raw Python script, using one simple API, we can create an Airflow DAG directly out of it that can then be checked by data engineers and put into the production environment, right? So without further ado, I'm going to turn it over to Andrew for a demo.
Cool. Yeah, let me get the right tab set up. Yeah, so basically this demo is going to be showing a lot of what Doris said and just explained as capabilities of Linea Pi. So the example that we have here is we have this Jupyter environment set up that's supposed to be our development environment, and we're going to try to come up with a setup that predicts house prices. And yeah, so let's just dive right into it. The first thing that Doris pointed out is basically Linea Pi's runs in the background. The only line that you really need to get all the capabilities is this import Linea Pi line. Yeah, and that's it. Now we're set up and ready to do our work. And so the first thing that we're going to do in this demo is we're going to read our training data, and then we can inspect it. And we see that there's a bunch of examples here of houses, their different features and their price. And so I'm going to go through the rest of these cells here really quickly, but essentially what we're doing is we're doing exploratory data analysis, EDA, and data munging. And so, we're going to be looking at stuff like, pair plots or correlations between features, right? And you can imagine basically in this example right now, I may have run that cell twice, sorry, that we are, really trying to understand our data. We're exploring different branches, looking at the features, seeing what's important for us, and, trying to come up with a clean training data set, right? And here, maybe at the end here of this section, we have a training data set that we are happy with. And like Doris said, what we can do is we can actually have Linea Pi save this training data, and that'll give us a lot of the benefits that Linea Pi gives us. Just to quickly demonstrate one of them, we can print the clean code for a given artifact. So right now, if I say print the code for the cleaning data, the training data artifact, we can actually see that we get only the minimum set of code necessary to reproduce this training data without any of the code that generates the pair plots, which is not necessary, right? And this is because we understand, based off of the code capture, what's the minimum set of code necessary. And then just to continue this example, training data is only useful if you're trying to get insight from it. And so we're going to be training a model to actually predict the housing prices. And for this example, we just chose simple linear regression. Cool, model looks good. We're going to save this as an artifact as well. And here comes the really cool magic, which is this is the API that Doris talked about earlier to convert from the development environment to the production environment. And it's this Linea Pi.2 pipeline. And we're going to specify a pipeline to produce as outputs the two artifacts that we saved earlier, both the training data and the housing. And so as soon as I press this, Linea Pi is going to be doing a bunch of magic to understand all the code that we've put in so far and generate a pipeline that Airflow can understand. And the reason why I said Airflow is because we specified that the framework that we want here is Airflow. And you can swap this framework out for the other frameworks that we support. And just really quickly, we can see some of the files that we've generated. I think the most interesting one is this module file. We can actually see that we have two functions here. One of the functions is to get the clean training data, and the other one is to get the model. And if you look closely at the model one, it's actually parameterized to take in the training data. And this is because Linea Pi has recognized that there's a dependency between the model and the training data, and that it can refactor out the training data code so that the model code does not need to call it again. It can just use the training data as generated previously. And just to end the demo here, we have a Airflow setup here as well that automatically picked up on the files that we just generated from the two pipeline call. And just to complete the loop here, as a data engineer, you should be able to take the pipeline that was just generated and run it. And yeah, maybe we can spend like 10 seconds here and watch the tasks all complete. And this is basically in the background generating the training data and the model that we just defined in the Jupyter notebook previously. Yeah, that's the demo. Doris, take it away.
Great, thanks so much, Andrew. All right, back to here. All right, before I move on, do folks have questions? All right, we'll give everybody a second to absorb the magic that you just saw. While everybody's absorbing, I'll keep talking about some of the other use cases that you could use Linea Pi for. So Andrew has already shown us how we can use Linea Pi to solve the problem that there's messy, irreproducible development code, right? Using Linea, you would be able to automatically clean up the code, modularize the code, right? And one thing that's also really nice is that Linea Pi is sitting in the runtime. So that means when you have things like out of order execution for your notebooks, or if you have modified the state of a cell to the point that the end result of the notebook is not reproducible, Linea Pi can guard against that because we're recording the execution in every single cell as it happens. So when you call it LineaPi.save to get to the clean code, we're actually able to use the entire history to create something reproducible. And the other thing that we can use Linea Pi for is that a lot of times folks are developing components of the pipeline and then trying it out, right, iteratively. So there's a huge problem of getting your pipelines and development code synced up, right? So as we saw earlier, you can use Linea Pi to create pipelines directly from development code, which makes it much easier to create pipelines that are synced up with what's happening in the latest development environment. And the other problem that we're able to solve is that a lot of times folks have this golden notebook with secret recipes for reading data, for transforming data, for model training, so on and so forth, right? So it's a lot of times really hard to keep track of these frequently used code snippets, especially if you can't remember where that notebook was placed or if it's distributed across a couple different files, right? With Linea Pi, what you can do is you can actually use the Linea artifact store to save and retrieve reusable components. You can simply call .save on an artifact and use the code associated with that artifact to run computation in the future, right? And what's really nice about Linea Pi is that we also do automatic version control without you having to use Git. So every time you do a save, we are automatically bumping up the version, so you don't have to worry about overwriting old code, and it makes it really easy to be able to revisit different versions. And the other issue that we're able to solve is that a lot of times folks are switching between environments as they work, from one machine to another, from one person to another, from dev to prod, for example, right? And the data is not always accessible because a lot of times we're writing data locally to the environment. With Linea Pi, you can also use the artifact store that can be hosted in a centralized location to be able to share data and results. And this is a much lower effort than writing to a very specific file system, because you can swap out different backends for the artifact store as you see fit. And the way that the end user interacts with it, it's simply calling a safe on an artifact with a name, and they can retrieve using that name across different environments. And lastly, what we're also able to solve is the fact that a lot of times when we have an artifact, we don't have enough information about the lineage in order to reproduce and trust it. For example, if we have a model that was trained on a specific data set, before we deploy into production, we would want to know exactly what that training set was in order to trust that the model can behave well in production, and also to be able to reproduce it if necessary. Right, so we saw earlier in Antje's demo that Linea Pi is able to store the artifact along with the code in the same exact object, and that makes it much easier to be able to retrieve the context by which, and the metadata by which the artifact is created. And the other thing that we're also keeping track of as we automatically generate pipelines is that we can keep track of the relationship between artifacts and pipelines. And that also makes it easier for folks to trace what's happening on the production side in pipelines to what originally happened in development to create these artifacts. All right, so kind of a review of the Linea Pi end-to-end story. So first, we are importing this Linea Pi library into the development environment. Can be a Jupyter Notebook, can be Databricks, Colab, VS Code, or just plain Python script. As long as it's a Python environment, we're able to interoperate with it, right? And the first thing that we're doing is, as we observe what's happening on the development side, we're in the background building this linear graph by automatically capturing execution and using dynamic and static analysis of the program in order to build this graph that allows us to understand what's going on at a deeper level, right? And the second thing that we do is once we have identified an artifact of interest, folks can just call lineapi.save on that artifact. And what we create then is we're encapsulating the code, the value, as well as the execution context into a single object called the artifact. And then we can take a set of artifacts and put it into the toPipeline API in order to translate what happens during development, these raw artifacts, into production pipelines, such as Airflow, like what Andrew has shown you earlier. But we can easily specify different frameworks for Linea Pi to translate into things like Ray, DVC, whatever other environment that you have chosen for production or has chosen for specific purposes. All right, so folks are probably curious about what this graph business is all about, right? So at a very high level, it is a custom graph generated by transforming the abstract syntax tree with runtime states. Abstract syntax tree is what you get by parsing the Python code, and the runtime state, what we mean by that is all the variables and all the relationship between the variables and the runtime environment, such as the library versions and the Python versions. And what it does is that it captures data flow and performance analysis during graph creation in order to allow us to simplify future operations. For example, we can use this graph to do code cleanup, and we can use this graph to do modularization. It captures the source code, mutations, dependencies, and external side effects, and runtime dependencies. So it's a very powerful abstraction that's capturing a lot of different related entities, right? And here I want to call out side effects very specifically. So what we mean by that is when you have reading and writing to external systems like a database or a file system that are external to the Python environment, this is also something that we are keeping track of in the linear graph as well, in order for us to have a broader view of what's going on during the data science workflow. And lastly, what's really unique about the linear graph is that it captures all Python language constructs rather than DSL abstractions. There are a lot of tools out there that are drop-in placements for certain libraries. For example, you can use DAS to scale up pandas, whereas Linea Pi, we are agnostic to the libraries that you're using. We're agnostic to pretty much anything that happens in your environment, because we are analyzing the runtime state and the code itself. All right, so let's actually walk through an example of what that looks like. So at the top, you see a code snippet, and the bottom is the graph that's generated by Linea Pi, right? And here is a really quick workflow, and we'll dive deeper into this exact example in a second. So first, what we're doing is we're intercepting the execution of the Python environment in order to be able to track the state and the code, right? And the second thing we're doing is we're translating the code into the abstract syntax tree. Then we're traversing this AST in order to capture static information for creating these nodes. And then we're executing the nodes in order to track mutations of variables and external side effects. And this is also where we're establishing relationships between the different variables and the different function calls. All right, so now I'm seeing there's a lot of questions in the chat. And thanks, Andrew, for answering them. We'll come back to some of these at the end. So let's walk through this program to see how we're generating this graph exactly. All right, so the first thing we'll see is that for each of these import statements, we're generating import nodes in the graph. And the very first function call is pd.readCSV. And what we see is that for this specific function call, there is a function call node. And the argument that is taking in is the module name, get adder to get the function name, which is this readCSV. Right, so now let's move on. For the entire training statement, what we see is that the subgraph that led to this statement is everything that's, all the nodes that are the ancestors to this function call. And by analyzing this graph, one thing we can do is we can basically identify the set of lines of code that's necessary for producing this train variable, right? This allows us to skip all of the sklearn import statements since they're not relevant to the workflow yet. All right, and then now let's move to the second statement of adding a specific or rather transforming a specific column in the train data set. And what's really interesting here is that Linea is able to automatically realize that this is mutating the existing train data frame. And then this allows us to create a relationship between these two statements so we can actually establish that dependency properly. If we don't do something like this, we will erroneously cut the dependency because this call itself does not make an explicit, this assignment itself does not make an explicit call to train. All right, so that's a quick walkthrough of an example of how you generate the code. And just to kind of recap everything, there are some key concepts in Linea Pi. The first one is an artifact. What it is, it's like we mentioned earlier, it's any intermediate result from the development process. So that means you can point it to any Python variable. You can also point it to any side effect operations, writing to disk, writing to other databases, and so on and so forth. It is something that we can track the state of as well as the code of. And the code for the artifact can also be parameterized to be used as a function. This is what we talked about a little earlier, where you can reuse some of these frequently used functions by saving it as the code to an artifact and then parameterizing it. And then there's the concept of an artifact store where you're saving all these artifacts as you work into a centralized location. It is a repository for the artifacts and their metadata. Metadata can include the creation time, version, but there's a lot more that goes into this. It is globally accessible across sessions, projects, and teams. And this is where we makes it really easy to be able to share across environments, both the value and the code. And then there's a concept of a pipeline, right? A pipeline is created by folks calling the two pipeline API on a set of Linea artifacts that they have specified. As we saw earlier in Andrew's demo, the pipeline that we create automatically modularized code based on shared subgraph between multiple artifacts. And we can transpile this to different orchestration environments, such as Airflow. And then we'll also talk a little bit more about how MLflow integration, what that could look like. And just to revisit the second point about modularizing code based on shared subgraph. So imagine we have two artifacts, A1 and A2, and they have a little bit of shared code, right? And what the modularization behavior looks like is that it'll first extract out this common code, and then it'll basically take out the code that's adjacent to the common code and creating a workflow that looks like this. So you don't have to recompute the same intersection twice. All right, so in terms of integration, so far we have implemented Airflow. We're currently actively working on Ray, MLflow, DVC, and on the roadmap are Kubeflow and Argo as well. And if you have suggestions for other frameworks that you would like to see integrations for, please put them in the chat. And the really cool thing about Linea Pi is that it's actually not that big a lift to create new integrations because of how well we have designed the abstractions. Right, so we heard that folks are probably really interested in MLflow specifically. So we wanted to dive a little bit deeper into what that integration looks like. So there are three key ways how MLflow, how Linea Pi can complement MLflow. The first way is that we can automatically create modules for MLflow pipelines. MLflow pipelines, I think, is a new feature that's been introduced recently where you can create, basically a pipeline, I think YAML file by stringing together different modules, but the current tool still requires users to define their own modules. With Linea Pi, we can create those modules for you automatically. And the second piece, of course, is that because we are seeing the entire Python environment, we're not a DSL, we're able to track lineage between models and training data. And right now in MLflow, training data is outside of their API, so it's hard to see those relationships. And lastly, we're able to capture the source code for model training. So this is where we can answer questions like what sort of hyperparameters this model was trained on, especially when those things weren't explicitly logged to MLflow. All right, so that concludes our presentation. Happy to answer questions. And also, please check out our social, and please go take a look at our GitHub and try to break the tool. That's what we're looking for. Folks, give us feedback and let us know how we can improve.
Perfect. Thanks so much, Doris and Andrew. Really enjoyed this talk and the demo here. And we had a good discussion here going on. I think Andrew did a good job already in answering most of those. People are curious about a little bit the model serving support maybe in the future, how to work with distributed training, distributed data loading, knowledge graphs. I think you covered in detail, Doris, here. Question about the integrations and support. You just showed the slide of what you're working on right now to integrate with from an orchestration and pipeline perspective. Question here, if you're looking in integrating with cloud-specific orchestrators, we have step functions on AWS. There's a question with Azure Data Factory. So any plans around there with future integrations? Are you looking for feedback from the community, what they're most interested in?
Yeah, so DVC and MLflow, they both came from the community. So we're definitely keeping our ears on the ground in terms of what folks are looking for. Open source tools are easier for us to integrate with, but it's not impossible to integrate with cloud-specific solutions.
All right, perfect. Yeah, I think, Andrew answered most of the questions, put out links here to the documentation as well. And let me see. Yeah, question, what does the integration with Ray looks like from Jules?
There is actually open PR on our GitHub repo right now. And we've been working with a couple of folks at AnyScale actually to work on that together. So I think one really interesting that we've done was we can automatically do our modularization and then translate them into Ray DAGs. And I see one question about DSL. So DSL stands for domain specific language. So think of things like pandas, Dask, and other things can be thought of as DSLs. They cover a very specific subset of operations within Python.
Perfect. Yeah, and I see another question. Yes, we are recording today, so the recording will be posted shortly. I'll put in the link here, or Chris, if you're online, put the link again in the chat. All right, thanks so much. We do have a full agenda today, so we have to move on. But yeah, thanks again, Doris and Andrew. Really enjoyed the talk. You put out the slide there, how to get in touch with you and the team if folks are interested in learning more about Linea. And with that, I'm handing it over to Neil. Neil, thanks so much for joining us today. And we will learn more about Ray Indeed and JAX and NVIDIA GPUs. So
Okay,
I'm excited.
great.
Take it away,
Thank
Neil.
you so much. Thank you so much for inviting me. Really, really happy to be here. Can you guys see my screen? I don't think it worked.
Not yet.
Here we go. Okay.
Here we go. Yeah.
Yeah. So yeah, thanks for inviting me here. I'm going to be talking about how we can run sort of multi-node trading jobs for large language models with JAX on SageMaker. So first, a little bit about myself. My name is Neil Vaithya. I'm a technical marketing engineer for deep learning frameworks at NVIDIA. As you might know, NVIDIA puts a lot of effort into ensuring that different deep learning tools run and perform well on GPU accelerators. And my job is to make sure that people know about the different resources that are available and hopefully make the tools a little bit easier to use. So let's get into the agenda. First thing I'm going to talk about is a sort of brief overview of what JAX is, if you're not familiar with it, and why you might want to use it. The next, I'm going to talk about multi-node execution and some of the benefits of using JAX for that process, and also talk a little bit about Alpha, which is a specific library that's built on top of JAX for model parallelism. And then finally, we'll get into a little bit of a demo on how we can run multi-node JAX jobs on AWS SageMaker. Okay, so first off, what is JAX? So at its core, JAX is a Python library for accelerated numerical computing, especially for machine learning research. And in particular, I think it's helpful to think of JAX as analogous to NumPy, but with a couple of key extra features. In particular, JIT compilation through XLA, which makes it possible to run JAX code on a number of different accelerators, including, of course, GPUs. Autograd, which enables you to automatically calculate gradients and makes differentiating code much more simple. And a couple of different facilities for parallelization of code, which we'll talk a little bit more about over the course of this presentation. So here we have a very simple neural network that's written out in regular NumPy code, and we'll take a look at how using JAX can sort of accelerate the code that we have here. So because it's NumPy, it's going to be running on a single node on our CPU, and just by switching over to JAX.NumPy, which is sort of submodule of JAX, so you can see all we've done here is replaced this NP with JNP. And now our code can automatically run on GPUs without us having to make any other changes due to the compilation with XLA. In addition, we can very easily calculate the gradients of these two functions using this grad function here. And this will allow us to create a function to calculate the gradients of our neural network with respect to the loss just by using this function here. So right out of the box, JAX includes a lot of tools that you would need to do deep learning in general and create neural networks. But just like people tend not to write neural networks with base NumPy, there are a lot of tools that are built on top of JAX that make it even simpler to create neural networks and use various different higher level abstractions that make the creation of neural networks a little bit simpler. And there's a bunch of them, right? So, OptX, Flax, and Haiku tend to be some of the more popular ones. There's GRaph for graph neural networks, of course, Hugging Face transformers. And one that we'll be talking a little bit more about today is Alpha, and we'll get into some of the special features of Alpha a little bit later on in the presentation. Okay, so we talked about the JIT compilation, and we talked about the Autograd functionality of JAX. And one of the next things that we're going to talk a little bit more about is the facilities for parallelization of code with JAX. And it's actually really simple to run JAX code in parallel across multiple processes, multiple processors, multiple different instances, multiple different nodes, a lot of different flexibility and variety that you can use to run JAX in a distributed manner. And so the first thing, I'm going to show a very simple demonstration of running JAX on 2 different nodes and kind of do the sort of most convoluted possible way of adding 1 + 1. But I think it's a good explanation of sort of what's going on behind the scenes when we're running JAX in on multiple nodes. So hopefully you can see here, we've got 2 different IP addresses. These are 2 instances of Jupyter that are running on different EC2 instances. And the first thing we're going to do is import JAX, and we can see that that runs instantly on both of our nodes. And the next thing that we're going to do is run this block jax.distributed.initialize. And what this does is it kind of creates on our sort of head node a server that listens for all of the other JAX processes that we might be running in our cluster. And we give it this coordinator address to tell it that this is going to be the sort of head node that's going to be listening for our other processes. We're going to tell it the number of different processes, in this case, just 2. So it knows when to, when it has, heard back from all the other processes, and the process ID. In this case, this is our first process, so this is going to be process ID 0. So I'll run that, and you can see that this code block just sort of hangs, because what it's doing is it's waiting to hear from all of the other JAX processes. And so on our second node, what we're going to do is run basically the same code. The only difference here is that we have a different process ID to indicate that this is our second process. And when I run that, you can see that, okay, on both of the nodes, the execution completes, which tells us that, okay, JAX is ready. It has sort of heard back from all of the distributed processes that are running, and we can continue on. And so I should note that right now both of these nodes are single GPU nodes. So they're, I forget the exact instance, but they both have 1 GPU associated with them. And when I run jax.devices, and again you can see it hangs because it's waiting for the other process to run. So I'll run it here. You can see that it actually shows up with 2 different GPUs, because what it's doing is it's recognizing that I have JAX running on 2 different nodes and 2 different processes, and both of them have access to 1 GPU each. And so in fact, if I go and run this second command, jax.localDevices, you can see that the process that's running on the first node only has access to 1 local GPU. And similarly here, we have access to 1 local GPU. So what I'm going to do is basically create an array that has the same length as the number of local GPUs that I have, and just fill it with 1s. In this case, because I have 1 local GPU per node, it's just going to be an array of length 1. And so we can see that, and I've run that on both of our nodes. And because this is just creating a local array, both of those ran instantly without having to wait for the other node to run that process. And then the next part here I'm going to do is use this function called jax.pmap, which sort of enables us to run whatever code that we put as our sort of function in the first argument. It compiles it and distributes it across all of our different processes in order to run this function in parallel. And so the function that we're actually going to be running in parallel is this function jax.lax.psum. And what this is a what JAX refers to as a collective function. And what that means is that it's going to basically do an all reduce, where it looks at what the values of this this vector is on each of our different nodes, and it'll combine them all together. In this case, it's going to be doing a sum. So it'll sum across all of the different nodes on all the different vectors on all of our different nodes. In this case, we only have 2 nodes, and sum them together. So of course we have an array of 1s on each of our nodes. So ideally what we should see is when we run this code, they'll get summed together, and we'll see an array of length 1 with a 2 in it, indicating that our arrays have been added together. So I'll run it on the first node, and we'll see again it's hanging because it's waiting for the second node. And I'll run that here, and that's exactly what we see. So it's a very simple example, obviously, sort of a trivial, operation, but hopefully this gives you a sense of, what it's like to run different or to run actually the same code on multiple different nodes and kind of, combine all of the results together. Now, in particular, doing this manually is a little bit cumbersome, right? I mean, we wouldn't in practice want to have to like SSH into each of our nodes and then specify, the particular IP address and what the number of processes is and our different process IDs. Ideally, we'd want something that kind of takes care of that automatically. And in the GPU case, there's a couple of different tools that we can use for that. In particular, Slurm and Ray, which will make it a little bit more straightforward to set the communication parameters within our cluster and execute the same code on each of our nodes so that we know that it's running across all of our different nodes. And using PMAP, what we saw when we use PMAP is that we're running the same code on each of our nodes. And that can be really helpful when you're having to do something like data parallelism, where you run the entire model on each of your nodes. And basically, you're splitting up your data and running a different portion of your data on each of your nodes. But with some of the largest models, that's actually not enough, because it can be, and if I go back to here, the size of models has been increasing to the point where you're not always going to be able to load an entire model up onto each GPU. And we can sort of see, in the past we were able to fit the largest model on a single GPU, but nowadays, even just to sort of load our models up and store them in GPU memory, we're going to need to have multiple different nodes. And there are a ton of different ways that you can sort of partition a model across different nodes. And that could be, an entire conversation, probably could be an entire conversation of in and of itself. But in particular, just to sort of give a, very brief overview of Alpha, what Alpha does is it looks at the sort of topography of your entire cluster. And in particular, you'll see that, within a node, you might have multiple GPUs that all have fast connections. And then across nodes, you'll have relatively slower connections. And there are different kinds of parallelism that you can use to partition your model up. And Alpha will sort of automatically partition up your model to take advantage of the fact that some of the connections are faster and some of the connections are a little bit slower. So I know that was a lot of different things that we introduced, but just to sort of recap what our demo will be showing. We have 4 different nodes that are all sort of managed by Amazon SageMaker. We're going to be using Ray to communicate across all of these nodes. And we'll be using Alpha as the library that we're writing our actual code in. And of course, as we mentioned before, Alpha is a library that's built on top of JAX and uses some of the features of JAX, like the autograd and the compilation and the parallelization to make that whole process a little bit easier. So let me pop over to our SageMaker notebook. And I know we don't have a ton of time, so I'll try and go through this relatively quickly. All of this code is available on GitHub, and we'll share a link afterwards if you want to inspect it a little bit more closely than we have time for right now. But basically what we're doing here is we're running this sort of pre-processing step on our SageMaker notebook. And then once we have all of it, let me zoom in a little bit. Hopefully it's a little bit better. Once we sort of run all of this pre-processing stuff on our SageMaker notebook, we're going to send all of our data and our model training code over to our SageMaker training nodes. And in particular, we're going to, like I mentioned, parallelize it across 4 different nodes. So here we're downloading the data and training the tokenizer. And just to save time, I'm just going to scroll through here without actually running the code. We're splitting our data into train and validation sets, and then we're going to save it to our disk. And then using Hugging Face, we're going to do the Hugging Face transformers library. We're going to download a GPT-2 configuration file, and we're going to save that as our Norwegian GPT-2 model that we're going to train. and I probably should have mentioned this, but what we're training with Alpa here is a GPT-2 model on Norwegian text. Okay, and so to actually launch this through SageMaker, we're going to import the SageMaker Python SDK sort of client library, and we're also going to import the Hugging Face specific facilities for SageMaker. We'll need a couple of different things that are SageMaker specific, like our session and our role and an S3 bucket that we're going to upload all of our data to. And we have our config data, which is basically, the scripts that we'll need in order to run on each of our different nodes. And our S3 data, which again, we're uploading to S3, which is all of our text data in Norwegian that we're going to be actually using for the training. We specify a bunch of different hyperparameters, which are specific to the kind of model that we want to train. In particular, we're going to be running sort of 2 different training epochs. And then we create this Hugging Face object here, which is, again, sort of specific to SageMaker. And this tells us, what version of PyTorch and what version of Hugging Face we're going to be using, what instances we're going to be running on, which in this case is these G5 12x large, which each have 4 GPUs. And we're going to be running 4 instances of, 4 instances each of those, 4 GPU nodes. And then all we have to do here is run this, estimator GPU alpha.fit function, point it to our input data and our config, and then, wait to tell us that, okay, this is going to come back immediately and not wait for the whole thing to train. And then very quickly, I'm also going to just show you guys what is in the sort of config. So there's 2 things that or I guess 3 things that we need. There's this requirements.txt file, which when we include this in our config, SageMaker will sort of automatically download all of the packages that are in this file. So you can see we're downloading Ray and Alpa and JAX, along with some other things, CuPy, Flex, and Optax. And then we have this SageMaker Ray helper script, which will be used to create the Ray cluster itself. And so again, there's a couple of things here. For example, you can see we're getting a list of all of the different hosts in our SageMaker cluster, and then we're specifying one of them as our master host, which is going to be the sort of controller of our entire Ray cluster. And then we have a function here that will actually start the Ray cluster and assign roles to all of our different nodes. And then the actual training script itself. This again comes from Hugging Face, so it's very similar to something that you would see as a Hugging Face Flask training example. There's just a couple of things that we had to add. So here we're running that code from our previous file to actually start the Ray cluster, and then we're adding a couple of different things that specify again where our data is and where we want to output our data to. And so the final thing is the alpha.init cluster Ray. And this replaces the sort of jax.distributed.init function that we saw in our sort of simpler example. And you can see that we don't, have to specify all of our different IP addresses and all of our different, what the node indexes are and things like that. We just have to run this one function, and it initializes our cluster and sort of, sends signals to all of the different nodes that tell us that these are, the things that we want to run on each node. So, and then the rest of this is all the sort of, the training script. I probably don't have time to get into all of it. So again, definitely check this out if you're interested in. But very quickly, I'll just show you, I ran this, I think, yesterday, just to, go through exactly, to see an example of what the output looks like. And you can see that, what you'd expect to see, our loss sort of decreases over time. And we have, pretty high throughput and teraflops per second, 22 teraflops of training throughput in running across our multi-node cluster with 4 different nodes. So that's pretty much it for the demo. I just wanted to quickly close out on 2 things. First of all, we are going to be releasing a JAX container from NVIDIA that you can use instead of having to sort of download and sort of set up your environment on every run. It'll be a little bit easier to just to pull this container, and we're going to be testing all of the libraries and making sure that everything runs well together. And if you're interested in helping us out and joining us in developing JAX for GPU, we are hiring. So if you're interested in JAX and you're interested in GPUs, definitely reach out. We're ramping up our support for JAX, and we'd be happy to have you. Yeah, that's about all I had for today.
All right, thanks so much, Neil. That's super exciting, the demo. I put in the GitHub link, folks, in the chat. So if you want to check out the notebook and the great stuff here that the team has done. Yeah, cool, thanks. We did have a few questions, and feel free to drop in more questions here in the chat, everyone. And I see Santa started to answer it as well, like when to decide basically to use JAX, right? Are there any like sweet spots, use cases you think it's a great one to actually use JAX?
Yeah, I think Santosh put this here, but I'll just reiterate. It's definitely really a useful tool when you need to distribute your training or your processing across multiple nodes, specifically for deep learning training. We looked at it a little bit, but there are a lot of different functionalities and facilities within JAX that make it pretty straightforward to do distributed training across multiple nodes and across multiple accelerators.
Right, yes, and there's a follow-up question. Is JAX an NVIDIA local development or spin out?
Yeah, that's a great question. Yeah, so JAX is a sort of a research framework out of Google, and so it's not just NVIDIA specific. It runs on a lot of different accelerators, including TPUs and CPUs and GPUs. We're specifically, of course, very interested in making sure that it works really well with GPUs, and so that's our involvement there.
All right, and yes, JAX uses XLA. Great stuff. Any more questions? Let me see. Yeah, Chris, if you're around, do you have any more questions? I know you're always curious.
Yeah, no, I think there was a lot of good info there. I still honestly don't feel like I fully understand JAX. And saying JAX, uses XLA. Yeah, I mean, I understand that, but I know that there is a group with a pretty famous developer advocate, Paige Bailey, that's I think now a PM over at Google, working with Jeff Dean directly on JAX. So that's why we want to pay attention to this. I guess I'm trying to understand, are people using JAX? Is this like Swift on top of TensorFlow that really didn't go anywhere? What, like?
Yeah, no, it's a good question. I think Santosh also might have some good insight on that, but we're definitely seeing JAX being used a lot for in research in particular. It's a little bit less common in production. The sort of inference story isn't necessarily as strong in particular, but it's definitely something that we have seen a really big increase in the usage of recently. Yeah, Santosh, I don't know if you had anything you wanted to add there.
Yeah. So I think it's worth pointing out a lot of the new transformer-based models do require, especially the large language models or multimodal, like diffusion-based models, do require multi-GPU for training and in some cases even inference. So that's really where we're seeing JAX moving into production. There's a ton of work in the physics ML world as well with JAX. So combining physics with neural networks to create new types of models and use cases.
Okay. And I like the description that it's sort of like a drop-in replacement for NumPy. It kind of reminded me of Numba and some of those libraries, but I think this is even broader because this is distributed training and has the XLA support as well too. So someone asked, is this based on TensorFlow or something? Is this like a clean rewrite that just goes directly to like XLA, or I mean, is it a parallel project to TensorFlow and PyTorch? Would I choose between one of those three going forward the next year or two?
Yeah, so I think the way that you put it as sort of, goes directly to XLA is a good way of thinking about it, right? I mean, I think the sort of explicit goals of JAX is something that compiles directly to XLA and has autograd. Those are sort of the two main things. And then of course, as we talked about, some of the parallelization stuff. So in particular, it's NumPy that runs on accelerators and has automatic differentiation. That's kind of the main goal of JAX, and I think that sort of leads to a lot of downstream applications of the framework.
Yeah. So it's kind of stripping away some of the complexity of TensorFlow, PyTorch, and just appealing to NumPy. And then can I plug this into like pandas that uses NumPy? Does pandas get an instant speed up if I can swap it in?
Yeah, I don't know the answer to that. Yeah, I'm not sure. There may very well be projects that sort of build on top of JAX to offer a sort of pandas interface, but I'm not familiar with any.
Gotcha. Okay, cool.
All right. And I think there's one more question on the dependency. So do I need a framework like Ray as a dependency for distributed training clusters with JAX?
Not necessarily. JAX includes all of the features like, the ability to run on accelerators, the ability to automatically differentiate, the ability to distribute across multiple nodes. You can do all of that with base JAX. Some of these frameworks that are built on top of it make it a little bit easier, and like Alpha incorporate some other functionality, like being able to do model parallelism and sort of have higher level abstractions. But you could do all of this in just in base JAX or JAX.NumPy.
Cool. And also, I think it's worth noting that there may or may not be a blog post coming up on this topic as well too, right? So hopefully we can get that out before the end of the year or something like that. So awesome.
Sounds good.
All right. Yes. Let's wrap it here. Thanks so much, Neil and Santosh. Really insightful to see and learn a little bit more about JAX, Ray, and how it all works together. Thanks so much for your session. And with that, let's switch over to the third and last session for today. I'm super happy to introduce Ganapati. He will talk about how to integrate SageMaker Data Wrangler or data prep service with MLOps workflows. So Ganapati, thanks so much. And yeah, take it away. You need to unmute yourself too.
Hey, thanks everyone. Thanks for sticking around. So I'm Ganapati Krishnamurthy. I'm a senior machine learning solutions architect with Amazon. I've been with Amazon for close to 4 years now, based in the Southeast area. So really happy to walk you through this quick presentation and a demo on Wrangler and the MLOps workflows integration part of it. Let me quickly share my screen. Can you see my screen?
Yes, we can see the slides. If you go maybe on full screen there.
I'll quickly, I don't have a lot of slides, just one or
Okay.
two. I'll switch on to the demo. So we'll spend a lot of time on the console. So the main objective of this session is to socialize our blog post that provides a detailed description on how you can integrate Data Wrangler with MLOps workflows. So I'll quickly talk about what is Data Wrangler and what are the MLOps integrations that we are going to see as part of this session and also as part of the blog and the associated Git link. You might be familiar with this machine learning lifecycle. So again, as you can see, there are a number of discrete steps involved here. So you start with the problem definition, and as data scientists, you must be spending a lot of time, and industry average is about like 70 to 80% of a data scientist time is spent on data preparation, which is about like collecting, analyzing, and preparing your data to feed into your model. And then comes your model training and tuning and deployment, and it doesn't end there. So you need to again like operationalize and monitor your models. So whenever there is a drift or when the performance degrades, you can kick off a retraining pipeline. So the real world problem that we see often is that as data scientists continue to operate in R&D mode, which is of course really essential. So there is a gap between a controlled workflow automation and the exploratory mode, right? So that is where MLOps really kicks in. So MLOps gives you the ability to move from an exploratory R&D mode to a controlled workflow orchestration methodology. So you'll be able to automate all of these discrete processes and put them in sequence and have visibility and traceability on each of these. Again, for the purpose of this conversation and also for the purpose of the blog, so I just wanted to mention that MLOps can mean like several different things for different people. So like some people associate MLOps to like, of course, workflow orchestration, and also with respect to like tracking your lineage or versioning your models, maintaining your model registry, and like cross-account deployment and so on. But for the simplicity of this conversation, and also to understand it simply, so we are just going to focus on the workflow orchestration part. We are not going to touch on the other areas. So for us, it's just the workflow orchestration that we're going to look at today. So again, as you know, with Amazon, we always start with a use case. So the use case that we are going to take for today is a simple claims fraud use case, a binary classification mechanism where we want to predict if a claim is fraudulent or not. So of course, as you can imagine, we are going to have two data files, a claims file and a customer's file. And then we are going to use Data Wrangler to actually like prepare our data files. So Data Wrangler is sort of like a low-code, no-code feature of SageMaker, which allows you to visually interact with the service, like a drag and drop feature, and you can build transformations in the form of a flow file with just few clicks. So once you have a flow file generated from Data Wrangler, then we are going to really look at how you can integrate it with some of the common workflow patterns. So we are going to talk about SageMaker pipelines, which is again part of the SageMaker Studio and is very well integrated with Data Wrangler. We are also going to see managed workflow for Apache Airflow, which is Amazon MWAA. So which again like provides you an environment where you can run Apache workflows, Airflow workflows. And then if time permits, I can also touch upon step functions, which is your state machines workflow orchestration, a serverless workflow orchestration. So again, there might be questions here on like, when do you need to use each of these workflow methodologies, right? So as you can see here, like pipelines and step functions are like pay as you go. So it's like you don't really pay for the service as such. So you just pay for the underlying resources that are generated and that are being used for the computation. Whereas your MWA is sort of like an environment that will be up and running, and that would, whenever you put a DAG file, it actually like picks it up and schedules your Apache workflow or runs it instantly. So that is probably sort of like a very high level differentiator. And when it comes to the use cases, again, like if you have a lot of like SageMaker related features as part of your ML pipeline. So for example, like your data transformation or like model tuning, feature store, everything is within SageMaker, then pipelines could be a great fit there because it integrates with most of the SageMaker features. And it is also part of your SageMaker Studio, and you can see the readily available integrations and navigate through it. So if you have a number of non-SageMaker related services, for example, like if you are running your ETL on Glue or EMR, or if you're loading to a Dynamo and so on, so then step functions could be a great fit there because step functions integrates with over 200 AWS services, and it is a serverless workflow orchestration mechanism. So that that could be a great option here. And of course, if you're already using Airflow, so by default, MWA might be your choice. And also Airflow provides you the portability. If you're really keen on like getting your workflows more portable and environment agnostic, then MWA might be a great fit there as well. So how would your data wrangler workflow look like? This is how it would look like. So again, like you can actually like start building workflows with just like few clicks. As I mentioned, you can join data sets, you can concatenate data sets, and it also provides you a number of transformations, built-in transformations that you can just leverage, or even you can build your own custom transformations. So let's get into the console and have some action here. I hope you can see my console. So again, this is the flow that we built for the claims fraud use case. So as you can see, I see you have a data wrangler workflow here. So you actually select your data wrangler from your studio, and you'll be able to come to the data flow screen here. Again, you can import your data sources. So by default, it's from S3. So you can also import from Athena. Data Wrangler offers connectivity to Databricks, Snowflake, and Redshift as well. So you'll be able to import your data sources from these resources as well. And then again, like all of these are readily available transformations. You can click on it and you can see that there is a data sampling done here for you. You can do some analysis with your data. So again, like you can generate histogram, bias report, so scatter plot, and the common analysis that you may want to do. And recently, Data Wrangler also added a training capability where you can actually like create a trained model out of autopilot. So you have your data prepared, and then you ask Data Wrangler, you configure a training job, it would create the model for you. So it would analyze like what would be the best algorithm and so on, and uses autopilot to do that, and also generates the underlying code for you. So coming back to that, to our flow, as you can see here, we are using a transformation to convert uppercase to lowercase. There are also several transformations that we have done. So even machine learning specific transformations like ordinal encoding, one-hot encoding, all of that is available here. So if you click on adding a step, you can see you can import custom formula. You can use a PySpark, Pandas, or a PySpark SQL code to build your own custom transformations. And of course, dimensionality reduction is available. So it in turn creates a model and that is trained to lower your dimensional space. So you also see like vectorizing your space, you're featurizing your text, handling missing values, outliers, and a whole bunch of readily available transformations that you can add with just simple clicks. Right. So what happens is now that because it is a flow file, it is stored as a .flow file. So it is also available as a JSON to the cloud. So you can actually like dump your JSON and you can start parsing the JSON and understand or extract the sources and then use it for your own integrations. That is what we are going to see as part of this session and the blog as such. So.
And Ganapati, can you zoom in a little bit? Can you make it a little bit bigger?
Oh, this one?
Yeah, and in general, I think the browser, yeah.
Okay. So, okay, all right. Is it good enough, or you want me to zoom even more?
Yeah, maybe one more, and I think we're good.
Okay.
Yeah, thanks.
So, first, I think there is a setup that we are doing here. We are just uploading the flow file and our input, as you can see, to S3, because as you know, SageMaker is highly integrated and S3 is a common default data source. So the setup part is just like really uploading your flow file and also your inputs to S3. And then the other thing that I wanted to show here in the Wrangler is that, so Wrangler also provides you a ready export, right? So you can actually export your flow to S3, or you can even like create a pipelines notebook. So what happens is it creates the entire flow as a processing step, and then it also adds optional training step and tuning step for you. So again, you can customize however you want. It generates all the code. So it's just like you need to just customize it and run it, or you can run the flow as such. And Wrangler also integrates readily with Feature Store. So when you actually export this flow to Feature Store, so Wrangler runs a processing job, and it also provides you the code that would actually ingest your features into a SageMaker Feature Store. So that is also available as a notebook. So it just like once you click it, you'll see a notebook with all the code. But again, in the interest of time, I'm not going into that. So for the purposes of this blog, so what we have done is we also wanted to show you how you can parse the JSON. So we are not using the integration feature of Wrangler that readily generates a notebook. Rather, we built a flow file, and we wanted to show you how you can parse it easily. That way, even it's not going to be just limited for these 3 workflows, right? So once you have a Data Wrangler flow file, you can integrate it with any ML orchestration that you want. So as you can see, we have the flow file URI here, S3 URI. We are just getting that and getting the names. And this is probably the meat of what we are discussing today, right? So you're opening the flow file, you're loading the JSON, and then so all of that is stored as nodes. So you can actually extract your input source names and input source URIs. And this is all you need to actually like build a workflow from here. So from here, we are building a Data Wrangler processing job. So as you can imagine, whatever we extracted from the source URIs, we are adding that as a processing input. And then we are also creating a processing job output. So Wrangler is going to actually run a SageMaker processing job behind the scenes. So you do that by actually retrieving your Data Wrangler container, which is available in the public domain. You can just use the URI retrieve and retrieve your Data Wrangler container. You configure your instances. And again, with SageMaker pipelines, you can also parameterize and pass this as parameters as well. We'll see that. So once you have the SageMaker processing job, so what you'll be doing is like, again, like there is a training step here. So we use XGBoost, and then we set up some hyperparameters. And then we are actually adding a processing step with the processor that we just configured. And then we are also adding the input and output. So once you do that, we are just like going to use 3 simple steps here. So we are going to use a processing step, training step, and registering the model. We are not going to go further ahead. So as you can see, we have a training step, and then we also have a registering your model. We are providing the instance configuration and the package name and all that. So with pipeline, as I said, you can pass parameters. So we are passing a string and an integer here, the instance type and the count. And then we are chaining these 3 steps that we created earlier. And then we are building a pipeline object. And then once you build a pipeline object, then all you need to do is just like kick it off. So you say pipeline.start, and it would actually like run the pipeline behind the scenes. And I have an example here. As you can see, we have 3 steps here. So all of these are executed successfully. And then if you click on it, each of it, you can also see what is the input, whatever we passed on in the notebook, and the output that it generated. And it also provides you the links to the CloudWatch for the logs. So whatever logs that the processing job is writing, so you can view all of it in the CloudWatch. So that is about integrating it with pipelines. Again, you can just generate the notebook from the Wrangler console and just use the notebook as is, or you can even build your own flow file if you have multiple complexities, and then use pipeline. And as we just saw, you can parse it, and you can build your own workflow from there. So that is about pipelines. So next, I'll quickly touch upon MWAA. Because I know that is interesting to a lot of folks here. So with Airflow, so MWAA, so again, you need to follow the same setup notebook. So you will be loading the files, and you need to also create a managed workflow Apache environment. So I will get to that in a minute in the console. So once you have an environment, so what happens is you have the requirements.txt that is uploaded to the S3 bucket, and then an environment is created with all the installations and libraries that you specify there. And we also built a custom Data Wrangler operator. So what this does is basically parsing the flow file here, whatever we saw on the pipelines, we are basically parsing the flow file and extracting the input and output. And we are also configuring the data wrangler setup for the processing job. And then, of course, we have a config.py and a ML pipeline.py that would actually trigger your Apache Airflow workflow here. So again, very much similar to what we saw earlier. So we build the requirements.txt and then we upload it. And then we also upload the data wrangler operator, which is just custom built. And you also need to provide some access for S3 and SageMaker for your role so that your job execution will not fail. And then we have a config here where we are passing all the parameters. As you can see, we specify our S3 distribution, input mode, the container. So you can, again, Data Wrangler provides container for different regions and it keeps getting updated. So you can look at the documentation and pick the right container that you want. And we are also passing the training configuration here with hyperparameters and the type of instances that we wanted to the training job to run and so on. So all of this is uploaded to the S3 bucket. And then this is your pipeline.py. So this would, again, like, as you can see, we are creating a DAG here. And then we are also configuring multiple tasks. So we have a config start to start, and then a data wrangler task that would, again, like, use the data wrangler custom operator. And then a training task where you'll be running the training and, of course, creating the model. So we are just like consistently only focusing on these three steps. And then once you have all of that uploaded, once you upload the pipeline, so you can go back to the SageMaker, the Apache Airflow UI and start running it. So this is your Airflow environment, as you can see here. So I already created an environment. So it is very easy and simple to create, as you can see. All you need to specify your requirements.txt. You need to specify your DAX folder and the usual AWS resources. You need to have a VPC, security group, subnets, and so on. And you can also create the Apache Airflow UI. You can configure it to be public or private. And then you can also enable your logs for your Apache Airflow jobs and so on. And of course, you'll have a execution role that we talked about. And then you can also add the access there. So when you click on the UI, so you can see the ML pipeline here. I have already run it. So you can see once we upload the DAG, so your pipeline gets kicked off and you can see the execution here. So, and you might be familiar with this, right? So we have run this multiple times and you have the logs here as well. You can look at the logs. So that is about Airflow. Again, I will quickly touch upon step functions. You might be familiar with state machines. So step functions is, again, like a serverless workflow orchestration. And we have a notebook for step functions as well over here. So it very much follows the same pattern. So except that it is using a SageMaker Data Science SDK. So this also provides you the same sort of like steps for like a processing step, a training step, tuning step, create model step, and inferencing step, and so on. So you can leverage the SageMaker Data Science SDK. That's what we have done here. So, and again, we are doing the same thing, right? We are parsing the flow file, we are configuring the processing job, and then we are using each of the step and we are chaining all of that together. And step functions also offers you ability to retry if there is a failure, or you can introduce wait and so on. So if you go on to the console, like you can see, there is a nice workflow that got created where you can track it visually. So we also have added a wait step here, and then like you can click and you can see the logs, the underlying code parameters, and so on. So that is about the integration as such. So again, like you can take a look at our blog, which is posted on the invite and also on the link. And we also have a Git repo like with all of these components that we just talked about. So I will stop it here and take any questions.
All right, thanks so much, Ganapati. Really cool demo. And I posted, for folks, everyone here, I posted the link to the blog post that Ganapati co-authored in here. If you want to read about it, maybe as a follow-up. And also I posted in here the GitHub link to the code repo. So, and if you have any questions, feel free to drop them in the chat window here. Yeah, Ganapati, I think you mentioned it briefly in the beginning, but maybe if you can give a quick summary. We heard the different orchestrators, right? You showed SageMaker pipelines. We see step functions here. There's the managed airflow workflows. So maybe on a high level, what's your recommendation between the different orchestrators?
So again, like as I said, it's always the use case that is going to dictate. So yeah, so if you are looking for like pay-as-you-go model, and if you have a lot of SageMaker integrations, then pipelines would be a great fit there. So yeah, if you are looking at ETL workflows where you have ETL component and you're using other AWS services, then step functions could be a fit there, right? So, and we see a lot of customers who are very specific about Airflow. They already have Airflow up and running, and they also are very keen and curious about the portability. Then Airflow MWA might be the great fit there. There are again, of course, other mechanisms, like if you're really into Kubernetes, if you're a kube shop, then Kubeflow might be a good fit there. But the purpose that we wanted to show is like how you can really parse your data wrangler and integrate it easily with other mechanisms. So it need not be just the three. You could integrate it with any other MLOps orchestration that you have in-house.
All right, got it. Perfect. And I don't see any more questions coming in here. So yeah, thanks so much, Ganapati. Let's wrap it up. And again, we've recorded today's session. So again, I'll put in all the links here in the chat to the Meetup group. The recording will be shortly available on our YouTube channel. And also just a quick plug for the November session. So we have the agenda already up there if you want to check it out. We will have another three talks coming up. We have Adi Pollack from Treeverse. She is talking about LakeFS and how it's the Git for data. So super excited there. We will hear from Infinster about their managed ML flow offering. And we'll also hear more about data mesh architectures. So feel free to join us again next month. And yeah, thanks, Ganapati, for the session and demo. All right, and with that, thanks everyone for joining, and hopefully see you next month.